Suppose we're being asked to find some critical values and we're given this limited information. How would we go about that? Well, the first thing you need to know when finding critical values is the type of test is determined by the symbol in the alternative hypothesis. So this tells me we're going to have a two-tailed test. And so our rejection region, we're going to have two rejection zones. And we're going to have two critical values. One's going to be negative and the other's going to be positive. And then these are our rejection zones or critical regions. Different textbooks call it different things. Rejection regions. And this is supposed to be symmetric, okay? So there would be two critical values. Now, alpha is the total rejection region area. And we've been told that alpha is 0.05. Since we have two rejection regions, and since this is symmetric, each of these rejection regions will have area alpha over 2. And 0.05 divided by 2 is 0.025. Okay. So to find these critical values, if I find this left one first, then I'll automatically have the right one. It'll just be the absolute value. Now, will our critical values be z-scores or t-scores? Since our population parameter is proportion, then our critical values are going to be z-scores. Z-values. Okay, so the command I'm going to need to use is that inverse norm command. Now, if you have an older model or just an 84 plus, you're going to need to automatically tell it the left area. So if I come here and suppose we just have a TI 84 plus, then you're going to go, let me get out of here. You're going to go to second and then vars, and then come down here to inverse norm, enter, and you must tell it the left area. So my left area here is 0.025. And then the default is it's a standard normal distribution. So I'm just going to come here and do paste. And then press enter again. And if I take that to 3 places, then my left critical value is going to be minus 1.960. And then by symmetry, I get that this right one is going to be positive 1.960. So if you have a CE model, then it's the same second vars, and we come down here to inverse norm. And you can see that you can actually have a choice when you have a CE model, but the default when you start off is left area. So again, the left area is 0.025. Paste that in. Okay, and we get the same answer. So for this one, we had two critical values, and they were plus and minus 1.960. So 1.960. All right, now what about this one? We look at the symbol in the alternative hypothesis, and so we're going to have a right tail test. So all of the rejection region is in the right tail. So we will have one critical value, and it will be a positive number. And again, our population parameter is a proportion, so it will be a z-score. Now, alpha is the area, the total area in the rejection zone, and so we only have one rejection region, and so this area is alpha. So now, if I go to just an 84 plus, I get onto second vars, and I come down here to inverse norm because it will be a z-score. I must tell it the left area. So this is left over from my previous. And the shaded region is the right area. But what we have to remember is the total area under this density curve is 1, and so the left area here is going to be 1 minus the shaded region. And you don't need to even calculate that. You can just tell it. The left area is 1 minus 0.01. And you must give left area when you're just on the plane 84 plus. You don't have a choice. And so the z-score, my critical value, is going to be, if I take that to 3 places, 2.326. That is my critical value. Okay. So we just have one. Here we have two. Here we just have one. Now, if you were using the other, if you have a CE model, you can actually tell it right area. So if I do second vars, and I come down here to inverse norm, so with the CE model, so this is from my previous problem, the default is left. But if I want to tell it the right area, which is 0.01, then I have to come down here and I have to choose the right. So with the CE, you can choose which tail. With the plain 84 plus, you must always give left area. And you see, I'll get the same thing. I'll get the same answer. Personally, I always give left area. So I get back in here in second vars because if you just, instead of chopping and changing and having to remember, if you just always give left area, then you don't have to worry about that. So I'll come back up here. And let's have 1 minus 0.01. It's my left area. And then I come down here and now I have to change it back to left. Okay, but you'll get the same answer. All right, so you notice how I got the same answer there. Okay. Going on to the next one. What happens here? Well, we can see that in our alternative hypothesis, we have a left tail test because the symbol is less than. So we will have a left tail test. We will have one critical value, and it will be a negative z-score because, again, our parameter is a proportion. So I'll draw it up here. All of the rejection region is in the left tail, and alpha is the total area in the rejection region. And here we're going to have 0.005. So again, I'm going to get that z-score. So again, I'm going to get into second vars, go to inverse norm, and I'm on left area, 0.005, and then just come down here and press enter. Okay, so I have one critical value, and it's going to be a negative z-score, which will be minus 2.576. Okay. All right, so let's go on to some others, two more. All right. Find the critical value obtained when using a 0.05 significance level. So that's telling you what alpha is. So alpha is equal to 0.05. For testing the claim that the mean is equal to 100. Okay. Well, it's the symbol on the alternative hypothesis that determines what kind of test we have. So the null hypothesis would just be equality there. It's always equality. And then when I get to the alternative hypothesis, I look at the symbol in the original claim, and it's not allowed. So for the alternative hypothesis, you can only have strictly less than, strictly greater than, or the not equal sign. So if the symbol in the original claim is not allowed, you take its complement. And the complement of equal is not equal. Now, in the alternative hypothesis, my symbol is the not equal sign, so we will have a two-tailed test. So what we're going to have is two rejection regions and two critical values. Now, alpha is the total area of the rejection region, and I have two rejection regions, so each of these regions will be area alpha over 2. So 0.05 divided by 2 is 0.025. We will have two critical values now. Are they a z-score or a t-score? And our population parameter is a mean, and we've been given the sample mean, and we've been given the sample standard deviation. We have not been given the population standard deviation. So sigma is unknown. And so when you have your population parameters, a mean with sigma is unknown, everything's going to be a t-score. So our critical values are going to be t-scores. So I'm going to get this left one, and then by symmetry, I'll automatically have the right one. So the command I'll need to use here is the inverse t command. And I'll give it left area. But then whenever you're using t-scores, you have to have degrees of freedom. And degrees of freedom is your sample size minus 1. And so I'm going to have 19. So I'm going to have that in my calculator. So I'm going to come over here. And I'm going to do second vars. And I'll have inverse t. I must give it left area here. There is no choice. Like with the inverse norm, you don't have the luxury of choosing. It wants the left area. So 0.025. And degrees of freedom are going to be 19. And so this t-score over here, this critical value is going to be minus 2.093. And then by symmetry, my second critical value will be positive 2.093. So we'll have two critical values, plus or minus t, well, they're t-scores, so t is equal to plus or minus 2.093. Okay. All right, and let's do our last problem. Last problem. What if I just change one thing about that problem? And I change the symbol. So my alpha is still 0.05, but now the claim is that mu is greater than 100. Of course, if we're going to do the null hypothesis, that's still the equal sign. But the important thing here is the alternative hypothesis. In the original claim, that symbol is allowed, so we keep it for the alternative hypothesis. And now the symbol in the alternative hypothesis tells us we are going to have a right tail test. So all of the rejection region is in the right tail. So there's going to be one critical value. It will be a positive number and it will be a t-score because we still have a population mean where sigma is unknown. So my critical value is a t-score. And all of my area is in this right tail. Okay, so I'm going to have to use the inverse t command, and I have to give left area and then degrees of freedom. Now, 0.05 is the right area. The left area is 1 minus the right area. So that's what you have to give it. Okay, so let's come here. And again, let's do second vars. And come down here to inverse t. It has my previous information. Now the left area is 1 minus 0.05. My degrees of freedom are still 19 because the sample size did not change. Okay. So I have one critical value, and it is t is equal to 1.729. So I only have one critical value, and it's a t-score. Okay. So I hope these 5 examples have kind of helped you to have a better understanding of how you decide if you're going to have 2 critical values or 1, and then which calculator commands you use with it. Okay. All right, so I'm going to stop the video now.